Assalamu alaikum and good morning. So today we continue talking about paging and segmentation, basically allocation of memory. One of the main topics of memory management. So we have covered paging and segmentation. Today we talk about related issues to these. One term is called trashing, the other called pre-paging. If you come across these two terms, then the meaning of trashing is basically the phenomena of a process having very frequent page faults. Okay? So in that case, we say that we have trashing. The process is doing what? Most of the time, having page faults. So if a process does not have enough pages, okay, the page fault rate is extremely high. Okay? This is something that we want to avoid. And how do we avoid something like this? By setting appropriate what? What would affect trashing? How can we improve this? Appropriate number of pages, right? Because based on Billy's anomaly, okay, if we set too many, also is not good, right? And what did we call that? The number of pages that are assigned to our process to execute with. We called it excellent, the working set, right? The working set. And what else also? What other things that really affects page faults? The replacement algorithm that is chosen, does it? Does it? When the replacement algorithm is called? After a page fault, right? Right? So when we have a page fault and we don't have an empty frame, then we call the replacement algorithm. Okay, so it's not a factor. However, what we're going to talk about today, okay, which is related to page replacement, okay, might reduce the page faults as well, the number of page faults. Okay, so initially a process starts with a certain number of pages, okay, and these pages, or a certain number of frames, let's say, right? And these frames are empty initially, right? Empty. So one way is to fill up these frames with certain pages, hoping that the process will be referencing addresses within these pages, rather than having page faults from the very beginning if the frames are empty. Correct? Yeah? We call this concept pre-paging. Pre-paging, which is filling up the frames that had been allocated to a process by a certain number of pages, hoping that the process will be referencing memory addresses within these pages. However, it might reference and it might not reference. So you are filling all the frames, right? So if the process referred to a page that is none of those already loaded in memory, then you have what? A page fault. And if you have a page fault, then what do you need to do? In this case, all the frames are full, right? So we have to call the page replacement to replace one of the pages in memory. And which one of them? That is based on the page replacement algorithm. But does that involve writing the page back? Do we need to write the page back? Or we don't need to? We don't need to, because basically this is a fresh page that has not been modified yet, right? That has not been modified yet. The ones that we loaded at the very beginning. We loaded pages and not yet being modified. However, also, here we have an overhead, which is calling the page replacement algorithm as well. So if you were not lucky at all, the referencing of the number of frames, say that we have 5 frames, the very first 5 references, they correspond to pages that are not in memory. Okay? So assume that that pages are pre-paged and alpha of the pages is used, the number of the pages, okay? Then the cost is S multiplied by alpha, okay? Saves page faults that is greater or less than the cost of the pre-paging. So we say that S multiplied by 1 minus alpha, S multiplied by 1 minus alpha, these are unnecessarily pages. And when alpha is very near to 0, then what? Pages is what? Pre-paging is what? Loses. Because alpha for us here is the number of pages that we loaded in memory and it had been referenced. So the 1 minus alpha is the one that had not been referenced. Okay? Now, in terms of finding out how many frames a process will be allocated, okay? There are different strategies, okay? And there is much more than what you see on the slide. But we have global replacement and we have local replacement. Okay? This is in terms of what? The frame that will be used for replacement. The frame that will be used for replacement. So if we have the frames allocated to a process, all of them occupied, and we have a page fault. In this case, we're going to call the replacement algorithm, and we need to swap out one of the pages and swap in the page that is desired, right? So far, we have been doing it using local replacement. Means processes are allocated a limited number of frames, and only the frames that are belonging to the process may be selected for replacement. Correct? However, in global replacement, we could select, or we call it steal, a frame from another process, okay? So this is called global replacement, and the other one that we have been practicing so far is called what? Local replacement. These are terms, if you have come across, you should be able to at least have certain understanding behind it. Okay. So the goal of the page replacement algorithm, or the goal of local page replacement algorithm, is to find what? The optimal working set. Okay, the optimal working set. Then the best number of frames a process can use that produces least page fault, right? So the working set is the minimal number of frames that the process actually requires in order for it to execute with a desired number of page faults. So the quality here is controlled. Okay, we have some bounds on the accepted number of page faults, and based on that, we need to find the minimal number of frames to achieve that quality. Okay, so this is the working set. Working set is related with a predefined quality, okay, desired level of the efficiency for the page replacement algorithm. These are some terminologies that might be useful while you're reading literature. As for allocating frames, the allocation can be done based on fixed frame allocation or priority allocation. Fixed frame allocation can be done different ways. Okay? One way is to give each process an equal number of frames from those available in the system. So if I have 20 frames and I have 5 processes, basically each of the processes will get 4 frames. Okay? So this is divide the available number of frames equally among the processes who are requesting these frames. Equal. Equal does not mean, okay, fair. Does not mean fair, because some processes might need much more memory than other processes. Okay, so another way is to use what we call proportional allocation. Depending on the size of the process, we allocate the number of frames. And the size of the process is identified by the number of pages the process has in its logical address space. Correct? Yeah? Right. So if we have Si to be the size of the process, and this is in terms of pages, okay? Then the sum of all pages needed by all processes equals to S capital. So S capital is the summation of all Si. And then if we have M processes, then the proportion for each process to be allocated frames equals to the size of it divided by the total size multiplied by the number of available frames. So if we have M frames and the proportion is half for one of the processes, then that process will take half of the available frames. Okay? On the right-hand side, like M equals to 64 available frames. S1 needs 10 pages. This is for the first process. The second process needs 127 pages. Then we calculate the proportion by 10 divided by 137, which is the summation of 10 and 127. That multiplied by the available number of frames, 64. That will be 5 frames for the first process and 59 frames for the second process. Clear? Okay. On the other hand, priority allocation also can be used. And here the proportion will be based on the priority of the process. So instead of the size, we use what? Priorities. And again, we need to know the range of the priorities that are available in the system, and based on that, set a proportion for each priority or priority range. Sometimes we can have sub-ranges of the range to give it certain portion of the available memory. Okay. Another thing that can be used with priority allocation is to select for replacement a frame from a process with lower priority number. So that's on the top of giving more frames for processes with higher priority. Also processes with higher priority, they can steal frames from processes of lower priority. So these were some of the terminologies related to paging, okay? And then we talk about one page replacement, which is called page buffer replacement algorithm. Page buffer replacement algorithm. The algorithm, the way it works, the system has a pool of frames, okay? And this can be used by processes in the system. So if we have a page fault, a victim frame will be chosen as what we did before for the page replacement algorithms. Now, we had a delay in the previous algorithms that we needed to do what? We needed to copy the victim page, okay, to the swap if it had been modified. And until that is done, we have to wait. And then after that, we do what? We swap in the desired frame. So that delay can be reduced. We can actually, instead, okay, choose one of the frames in the frame pool to bring in the frame that we need to swap in. So we don't have to wait for the page to be written. Do you understand? No? Right. We use, or we have duster here. I'll show you on the board. Okay, so assume that we have certain number of frames, okay, that are used. All of it are occupied. Okay? Now we have page replacement. The page replacement basically is bringing one page from the swap, okay, bring it in. But we have to select one, say that this is the victim, okay, so this is the victim page. We have to swap it out, okay? So this is in and this is out. Now, we said there is a bit here, okay, at least, okay, there are many other bits, right? It says that whether this page had been modified or not. Assume that this is 1, okay? So this is what? Modified. It's modified, this page. Modified means when I am to bring this page, I cannot overwrite it. First, I have to do this, write it to the swap, and then I write this in its place. So I have to wait. How long? The time needed to write this out. Okay? Now we can have an improvement on this. Okay? The improvement is by having basically a number of frames that are available in memory. This is the pool of what? Free frames. A pool of free frames available in the system for all processes. So what we need to do, immediately, we can use one of these frames. We can use one of these frames. So one of these frames can be used for this page, okay? And this page, this frame, is linked with the rest of the frames, right? So now we have the first, second, and fourth frame, okay? And here the third frame is replaced by what? By this page. So we have the process using 4 frames, okay? And this one, later on, can be what? Written out. So this is an improvement now. We don't have to wait, right? We don't have to wait until the page is written out. Now, how can we do this? In fact, what do you have in here? The page table, what is it? What is it? Table that holds frame numbers, correct? And this is a list, okay? This is what? A list. So I could have this, and then after that this, and then after that this. So this becomes isolated by itself, right? That later on will be what? Freed, written to memory, and becomes what? Free. When it becomes free, we will add it to where? So after we write, then we add it to this pool. So the address of this frame will be here within this pool, one of the frames that are available for the system. Do you understand this? Yeah? Okay. So this is an improvement. You don't have to wait for swap out operation. Now we can have an improvement on this by why we needed to write this out? Because of this bit, right? The victim page has been modified. Has to be written so that it becomes identical to what's in the swap. But if it was 0, do we need to do this process? We don't need to. So the enhancement is when the pager is idle, when there is no paging, do what? Write, okay, all of the modified pages, write it on the swap. And if I write it on the swap, then they become identical, right? Then I can change this modified bit to what? To 0, okay? So the enhancement is to keep track of the pages that had been modified, okay? So we have a list of modified pages, okay? So we know which pages that had been modified. When the pager is idle, then we do what? Write them. Write them and change their modified bit to what? 0. So we're gonna, all of these are what? Have a modified bit of 1, say. Some of them. But here, modified all of them, which are some of what the process has. Okay? So we're going to write them, okay, write to whom? To the swap. And if I write it to the swap, means they are identical with the swap. Then the second step, so this is number one, I write to the swap. The second is what? Is to change that. Change it to what? 0. This will reduce the probability in the future if we have swap, if we have a victim chosen, which is in the page replacement, right? Then most likely this victim is already written. We don't have to wait for it. Okay? Now there is also another enhancement. The other enhancement, okay, we need to get back to the algorithm. The algorithm says, okay, when a victim is selected and its modified bit is 1, pick up a frame out of the pool of free frames, use it, okay? And then write this page to the swap. So it's identical, right? I write it to the swap. But this is what? This is a frame in memory. I did not overwrite it, did I? Did I? I did not overwrite it. I just wrote it to the swap, and then it joins the set of free frames. So in the future, so this page, assume it's here, okay? This is the page X. In the future, if we have page fault, what are we supposed to do? We're supposed to pick up the victim, which victim is that, and then bring from the swap to memory. Swap to memory. However, that page fault might be, okay, a reference to a page that was before that. It was where? In memory. And it had been selected to go out, right? And where is it? In the pool, right? Is in here, correct? Because the algorithm says, write it, okay, add it to the pool, isn't it? So in the future, if we have a page fault, then instead of immediately bringing from the swap, first check. We need to check whether it is here in the pool or not. If it's in the pool, it's in memory already, right? This is memory, right? So I don't need to write it from the I/O devices. This is I/O, right? Okay? So by that, we are speeding up the process as well. And this page is fresh. This page is a duplicate of what already exists in the swap. Clear? So these are the enhancement for what we call the page buffering replacement algorithm. Any question about this? Now we mentioned that one of the page replacement algorithms is the LRU. And it's the commonly used page replacement algorithm. So if we are adopting it, we need to implement it. So what are the available implementations of this? Options to implement the LRU. This is what we will discuss. One way is to have a counter implementation of LRU. What does that mean? We need to have a logical clock, okay? So when the process starts, we have a logical clock. Logical clock, right? So the tick of it is the reference, okay? The time of reference, okay? That will be the tick. And then we have pages for a process. What we need to do is to keep track of what? The time the page was referenced. Because LRU is what? Least recently used. Okay? Least recently used means the farthest in time page being used is the victim. Correct? So whenever a page is referenced, write the clock to here. Okay? So we need to write the clock here. Okay? Right? When a page is referenced. Whenever a page is referenced, write the time at which is what was referenced to that particular page. Okay? So if this one is referenced, okay, page 0, then I'm gonna write the time for that. Okay? Say initially the time is 0. I write 0 to that. Okay? And this one, I write 1, I write 2, I write 3, and so on. Right? Whenever there is a reference, I can increment the logical clock that way. It's just a logical clock. Okay? Then, if I have page replacement, okay, so now if we have page replacement, what to do? We have to select one of these as a victim. Okay? So the victim, which one? The one that has the least in terms of the time it had been referenced. So this is what? Time reference. Right? Now this logical clock, okay, of course it has a particular size, okay, that, or max reading we say. Okay, it has a max reading depending on the number of bits, okay, that we use for that one. If it's a register, okay, it has 8 bits, so we have particular size, right? Now, if this process P0 has a reference string, P0, P process Px, okay, has reference string. Okay, it might reference, for example, 5, okay, 1002, okay, 29, blah, 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 right? It has a length until the last page that is referenced, say the last page that was referenced is 35, okay? It has a length, correct? Now, if this length is greater than, if this one is greater than what this can provide, then I might have what? An overflow, right? I might have an overflow because logical clock is incremented whenever there is what? A reference, right? Whenever there is a reference. And if the referencing of one particular, even here also, you might have that. If the referencing of one particular, but I would have it earlier here. Anyway, right? So that's one way of implementation. It's valid, it's correct, it's exact implementation. Okay? However, it has problems. And then, so we've seen that the problem of overflow. The other problem is what? You have to search. You have to do what? Search. Search to find what? Okay, to find the minimum. Okay, the minimum. So, it's time consuming as well. What are the other implementations? The other exact implementations of LRU is to use a stack. How is that? Well, we start like this. You put all the pages in a stack, and then what do we do? Whenever a page is referenced, we move it to the top of the stack. Okay? So I have a stack like this. And what are they? What do we have here? All the pages from page 0 until page n-1. Okay? When a page is referenced, okay, when I have a reference, so I have reference of page k, then if this is page k, what should I do? Move it to the top. Okay? Move it to the top. Move. Of course, this isn't how stack works, right? Okay? But if we could keep doing so, when a page is referenced, it's in the top, okay? So maybe PJ is referenced after that on the top, PI, and so on, right? So who will be at the bottom here? Who's here? The victim, right? The victim. Okay? But if we are to implement this in terms of implementation, this isn't really like that, right? So the way it's implemented is basically using what I call doubly linked list. Okay, let's say this is we call it the front, okay, rear, okay, or start in, isn't it? So what we do when a page is referenced, we put it first, right? So the page that is not referenced is where? The victim. So where's the victim here? This is the victim, right? So this is the actual implementation, okay, double linked list. And the last page, the rear, is what? The victim. And how can I get the rear? You don't have to do any search, right? Okay, so this is direct, right? Okay, direct. Directly. I don't have to do linear search or a search as in before. That's good. But however, this operation is expensive, okay? The operation is what? Expensive, which is putting here. Okay? So again, this isn't really something that will work well, okay, if we are to adopt the LRU. Then what? Well, the only solution is to approximate it. Approximate LRU. How would we approximate LRU? Different approximations. There are different methods of doing so. The very first method, it says you can use additional bits to keep track of the referencing of the pages. Referencing of the pages. The idea is like this. For each page, okay, we're going to have, okay, so this is reference bits, a number of reference bits. In fact, every page also, from time to time, what is it? It is either referenced or unreferenced. So here we have the reference, okay, the reference bit of the page, right? This is the page table that has all the pages. Some of it referenced, some of it not referenced. Remember that, the valid and invalid bit, right? Yeah? Okay. So what we're going to do is like this. We're going to keep track of the history, okay, of the history for all pages being referenced. But history might be too long, right? So we can't really keep track of everything, okay? So instead, we're going to keep track of a number of scans through history, okay? So we're going periodically, okay, periodically scan through this, okay? That's the algorithm. Number one, scan, where? Here. Periodically means what? Every, say, m units of time. ممكن تكون this m say 10 milliseconds. مثلا, right? Could be something like that. Any number that had been found is like doing okay based on simulation results, of course. So now, we have rounds, right? The rounds are like this. Okay, this is time 0, this is time m, this is time 2m, right? 3m, correct? And continues. At this point, I have readings. At these points, I would have readings. What are these readings? The readings are whether the page is referenced or not. Okay? So here, what do I have? Reference bits. So assume that I have 8 bits. Okay. Then what would I do? Initially, all zeros, correct? All zeros. Then, when a page is referenced, I need to do right shift by adding 1 from the left. Okay? So I add 1 to the left, and I get rid of the last bit, which is the first bit, depending on the whether you're using, okay, what coding is that, okay? So I have like 0 to 7, here are the bits, okay? You always add to bit 7, last bit, okay? And you get rid of the first bit, okay? So I have, if PK is referenced, then what? Then add 1 to ايش اللي هو high bit and get rid of what? Which is low bit, right? Get rid of low bit. Okay? So I'm pushing left to right. If not reference, then what do I do? 0, right? If not reference, then what? Add 0 to high and, well, remove low. Right? Low bit. Okay. So I'm doing that every m units of time. Right? This is time. Now, if I have a page fault, okay, what would I do? Now, if page fault, then what? The page that has the smallest is the victim. Correct? Because the page that has a 1 here means just being used, okay? At least within this interval time, right? Within a certain interval time. So if I have this as the string, okay, 4, okay, 1, 1, 1, okay, or I have like this, okay, or like this, which one is the victim? Which one is the victim? Tell me. The second one. Excellent. Look. So this one is the victim. Right? Why? It had been referenced in all the previous readings, but the last reading, it was not. Right? This one, it had been referenced in the last and the one before last. This one never been referenced, but the last reading was referenced. That's okay, right? It's not always I take it based on the last reading, of course. I take it based on numbers, I compare them. I could have something like this, right? Okay, 0, 0, 0, okay. All of them, right? But I have here like 1, I have here 0, okay, or I have here 1, 1, and so on, okay. Then which one is the victim? Okay, is this one. Right? So based on that. So we take the minimal, and since we have this bits representation, that's much easier to find which one is the minimal. Okay. Okay, so this is, okay, I explained it here, okay? This is additional reference bits way of implementing an approximation. Now, what if I find that the minimal is 2 pages? Then what should I do? Just select any one of them, right? Or actually you can free both of them and use one, right? So if you have 2 found to be the minimum or more, use one of them, the FIFO, the first one that you found, or basically you can free all of them and use one. The other approximation is, we call it the second chance algorithm. Second chance algorithm, the way it works, every page has a reference bit, whether it had been referenced or not. The way it works like this. If we have a page fault, then we scan through the pages. If the page is not referenced 0, then that is the victim, right? But if it's referenced 1, then what do? We change the reference bit to 0, and we proceed to find another one. Maybe after that we could find a page that has not been referenced, right? Hoping so. We keep doing this the same. If the page is referenced, change it to 0, its reference bit, and continue searching for a page that is not referenced. If all the pages had been referenced, then what are we doing? We are giving a chance for each page, changing the reference bit to 0, and then we get back to the very first page that we changed the reference bit to 0, and then choose it as a victim, right? So this is an approximation as well, okay? We favor unreferenced pages on those that are referenced, okay? And then since we're searching linearly, if we come across a page that is referenced, we change this reference bit to 0, hoping that we will find the one that is not referenced. Actually, we will, but it might be one of those that we changed, okay? So this is the second chance algorithm. And the last algorithm is the enhanced second chance algorithm. And in this algorithm, we look at 2 bits, referenced and modified. So if we're looking at these 2 bits, referenced and modified, that could take values 0 or 1, right? Which is the best victim? A page that is excellent. A page that is not referenced and not modified. And that is the main goal, okay? So the goal of the algorithm is to find first a page that is not referenced and not modified. If it's found, then that is the victim, and we're done. If it's not found, then we look for a page that is what? 0, 1. And 0 is what? Not referenced, but modified. Okay? But if we can't, then each page that we visit, if you find that its reference bit is 1, what do? Change it to 0. Change it to 0. So we look at the first bit, right? We look at the first bit. If it's 0, then we look at the second, okay? So, of course, if it's 0, we have already chosen it in the very first round. So it will be what? 1, right? So we look at this one. If it's 0, then that's the victim. Right? If it's 1, referenced. So give it a second chance. Change it to what? 0. Change it to 0. And then we repeat again if you cannot find. And for sure, doing so, you will get a page that is either, okay, 0, 0 or 0, 1. Okay, so that was the approximation of LRU. Hope that you understood that. There is another concept in your textbook also related to memory, which is basically mapped files. Mapped files, or memory mapping in general. As you know, and we're going to talk about the time we talk about file system, when you have a read from a file, if you're reading 1 byte, in fact, the actual read is not performed for 1 byte. It's performed for 1 block, right? With a size that's much more than that. And then it's cached in memory. Cached in memory. Why is that done? Because it's less expensive, right? Not for every byte I need to have an I/O read or write, right? So the next consecutive reads from the file, most likely they will be within that block. So if they are, that's great. We have saved many I/O instructions, and we save time. The same concept. So this is automatically done for you, without your interfering in this. The system does it that way. However, sometimes you might be coding, and you are using information from a file. And you think that a particular portion of the file, most of the time is what? Referenced. Most of the time you are referring to data within that portion, And that be multiple blocks, of course. So you want to speed up that. You want to speed up, dealing with that file. What do? You can get that portion of the file to be in memory at all times as long as your process is executing. So that's much faster, much better, right? And you can do so, by using the concept of memory mapped files, I said that since you have been doing lots of coding, since the beginning of the semester, and now you are busy with your project and gonna have homework as well, So we stopped giving you coding. However, this easily can be coded. Sometimes even you could map the whole file, The whole file. But this concept, keep it in mind. If you come across a problem like that in the future, the solution is, memory map the portion that you need of the file, or even sometimes the whole file if it's not too big or large in size. So that's the concept of memory map files. You don't reference any more disk, Instead, what do? You reference memory, That's a good stop point. So next time we talk about allocating memory using the body system and the slab, Don't forget, on Tuesday you're gonna have quiz, and on Thursday as well.